Good morning, champs. In thermodynamics, energy is always conserved. We write this using the energy balance. Delta E equals heat plus work. But something strange happens in reality. Hot coffee cools down. Compressed gas relaxes. Hot exhaust gases leave engines and lose their ability to produce useful work. So, if energy is conserved, why do systems lose their ability to produce useful work? The answer is exergy. But before defining exergy, let's compare two situations. First, imagine water at room temperature. It contains a large amount of energy, but it cannot drive a turbine or power an engine. Now compare this with high temperature steam. Steam also contains energy, but now that energy can actually produce useful work. So thermodynamics needs another quantity, not just the amount of energy, but also the usefulness of that energy. This quantity is called exergy. Exergy measures the maximum useful work obtainable from a system. Its symbol is capital E sub x, and its unit is joules. But there's an important detail. Exergy is always defined relative to the environment. So we introduce an ambient state with ambient temperature, T sub amb, and ambient pressure, P sub amb. If the system eventually reaches the same temperature and pressure as the environment, then no more useful work can be extracted. At that point, exergy becomes zero. Now let's look at a flowing system. We draw a control volume with inlet, outlet, heat transfer, and work transfer. First, we remember the energy balance. The rate of change of energy equals the energy transported by mass flow plus heat transfer plus work transfer. This balance tracks total energy, but it does not tell us how much useful work remains. To understand that, we need entropy. Real processes are irreversible. Examples are friction, mixing, and heat transfer through finite temperature differences. These processes generate entropy, and entropy production is always greater than or equal to zero. Entropy spreads energy and reduces the ability to convert energy into useful work. This is the key idea. Entropy destroys useful work potential. Now we can connect entropy and exergy. The exergy destruction rate equals ambient temperature times entropy production. So if entropy production increases, exergy destruction also increases. This creates a very important chain. Irreversibility creates entropy. Entropy destroys exergy, and exergy measures useful work potential. Up to now, we worked with total exergy, but for flowing systems, it is often more convenient to work per kilogram. So we define specific exergy. Specific exergy equals total exergy divided by mass. Its symbol is lowercase e sub x, and its unit is joules per kilogram. If we multiply specific exergy by mass flow rate, we obtain exergy rate. Its symbol is E sub x with a dot, and its unit is watts. Now we introduce the specific exergy equation. Specific exergy equals enthalpy difference minus ambient temperature times entropy difference. The first term represents energy above the environment. If the system is hotter, it has more useful work potential. The second term is a penalty caused by entropy. Entropy spreads energy and makes it harder to convert into useful work. If we now assume an ideal gas, we can derive the entropy difference using the ideal gas entropy relation. For an ideal gas, the enthalpy difference is C sub P times temperature difference. If we insert the entropy relation and the enthalpy relation into the Exergy equation, we obtain the ideal gas Exergy formula. The first term represents work potential caused by temperature difference. The entropy term represents the reduction in useful work caused by energy spreading. And the pressure term represents additional work potential caused by pressure difference. So the key takeaway is simple. Energy is conserved. Exergy is not. And entropy production destroys useful work potential.